And last time we were talking about simple, like very simple arithmetical functions on a Turing machine. I believe we talked about adding 1 to a binary number and also subtracting 1 from a binary number. I want to do something a little bit more interesting today. We also multiplied a binary number by 2, which is very easy. You just stick a 0 on the as the last digit. What about functions of several, as we would say in programming, several parameters? That is a function which takes 2 inputs and gives you a single output. This is a little bit more abstract, but actually this is a fundamental thing. For example, if I want to add 2 numbers together, that's what you're going to have to talk about. A function which takes 2 inputs and produces 1 output, such as adding 2 numbers together. Like, you know, I could write it as sum of 37, 42 equals 79, right? Something like that. This is super useful and an obvious thing that you would want to do if you're thinking about machines to compute numerical functions. This is a very basic example. All right. Now, how are we going to handle that? There are a few different strategies for how to handle this on a Turing machine. You know, the idea in general is you put the input on the tape when you start, and then the machine does some stuff using the input. Now, what's the input in this case? The input consists of 2 separate numbers, so you can't really put them both on the tape. I mean, you can't just write this on the tape because that's indistinguishable from a single big number. So typically you would do this, I would say there's basically 2 strategies that you can use. You can put, I will say you can, actually this is not the way that we're going to do it, at least for today, but we're going to do this at some points in the future. You can put both numbers on the tape with some kind of what they call a separator. That is, you just invent some new thing in your alphabet, which is not a number at all, but it's just used as like a placeholder to indicate this thing is different from this other thing. So, and that's the role of this comma here. You could say in this context, this comma is acting as a separator for the 2 parameters. More often, we are going to use, rather than a comma, just because a comma easily blends in with like words that I'm writing, we often use some separator like the this symbol, the hashtag, the hash symbol. So for instance, this one here, so this, if you were doing it in this way, you would write this on the tape like that. And then your Turing machine would include the hashtag as one of its alphabet symbols. And then, you know, as you're moving the head back and forth, you have to keep track of when I see the hashtag. That's how you tell the difference between the first thing and the second thing. All right. So that's one strategy that that actually, like I said, the stuff we're going to do today, we're not going to do it this way because there's a more convenient way to do things. So I'm going to say sometimes, in particular for adding numbers, which is really what I want to talk about today, sometimes it's convenient to what they call stack the inputs. For example, these 2 numbers, 37 and 42, they happen to have the same number of digits, which is convenient for adding them together. If they had different numbers of digits, you could just insert a bunch of zeros on the left to make them the same length. But anyway, these numbers we're going to write on the Turing machine sort of like this. Now that looks like a fraction. I'm not thinking of that as a fraction. I'm thinking of it just as if the 2 numbers are stacked on top of one another. So in the context of the tape, my tape would have, you know, blanks, of course, on the left and on the right, but I would put 3 and 4 stacked together and 7 and 2 stacked together. So these are not fractions, although that is how I'm writing them. They are just digits stacked on top of one another. Rather than writing them all in a big line with a separator, actually, I mean, hopefully you see where this is going. If I intend to actually add these numbers together, it is appropriate much more appropriate to think of them as digits being stacked, and then you add the digits one at a time. Whereas if you put it on the tape like this, then it becomes a very complicated thing to move back and forth constantly on the tape to go digit by digit. But if it starts off in this way, it's much more convenient. So for today at least, since we're talking about adding numbers, we're going to be stacking the inputs all the time. All right. So let's try some interesting binary arithmetic here. Eventually I want to talk about adding two numbers together, but let's do a simpler example first. Let's make a Turing machine for what they call bitwise AND. This is one of the fundamental operations on bits that you can do with like very basic circuits. You can make a bitwise AND gate. What that means is you combine two binary numbers. For example, here's an example. This thing and is like an operation. 10101. Bitwise AND. It means you combine these two strings bit by bit. That is digit by digit. And what you do in each digit is the logical AND operation, where AND means you sort of interpret the 0 as a false and the 1 as a true, and you do the ordinary Boolean AND to them. So the way that I would write this would be you compare them digit by digit first of all. So in this example, it is most convenient to stack them up. Oops, I wrote it wrong. I am lining them up like this, and then I'm going to, just in each digit do the AND. So I'm going to go digit by digit here, bit by bit, and everything up. Remember, the definition of AND is if there's a 0 involved, the answer will be 0. If they're both 1s, the answer is 1. That's how AND works. So the answer here, going right to left, would be 0, 0, 1, 0, 0. Right? That's the bitwise AND. Now, I did it going right to left just because I'm used to, adding with the Arabic numbers, and you should always go right to left in that case. But actually, when you're doing AND, it's not really necessary. The point of going right to left is so that you can carry properly. But the AND doesn't involve carrying. It's just purely bitwise. You never influence one bit with the next. So actually, this you can do it left to right if you want to. All right, can we do that using a Turing machine? This is my my goal for the next few minutes. Let's try to do this on a Turing machine. All right. First of all, I will say, what kinds of things are you going to see on the tape? So the tape starts off with sort of letters. The letters that you're going to encounter on the tape look like stacked things. They could look like zeros stacked over a 0. It could look like 0 and 1. It could look like 1 and 0. It could look like 1 and 1. Actually, those are all the options for what the tape has on it when you start. So the tape starts with letters that look like that. And then what's our strategy is you basically just sort of look at one of these things and you change it into the appropriate answer. So we want to replace them. We'll replace them with, for instance, if the tape really does have a 0 and a 0, I want to replace that with the answer of 0 and 0, which is 0. So this one also replaces with a 0. This one also becomes a 0. And this one becomes a 1. All right. So this is what the machine ought to do. You see one of those weird stacked things, and you replace it with the answer. All right, let's see if we can make it happen. Here's my starting state. I would like, for example, this thing right here. The way I would turn that into a Turing machine arrow would look like this: 0, 0, 0, and then I guess R or something. You move on to the next digit after that. But that's how you would handle that thing. If I read 0 stacked over 0, then I change that to a 0, which is the answer, and then move on to the next digit. All right. So I'm going to have an arrow that looks like this from here. Where should that arrow go? Should it go to another state, or maybe just back to the same state? Those are your choices, I suppose. I see some people making a certain motion with their fingers. I think it should go back to the same state. Actually, what I want is to do something like this, basically over and over again, right? You do this. This gives you the answer in that digit, and then you just move to the right and do the same thing again. So actually, this entire Turing machine is just going to be one state with a single looped edge. And what does the looped edge say? Well, it says this, and then it also says similar things for these other three possibilities. So it says 0, 0 becomes a 0 and moves to the right. What if instead it was 0 over 1? That becomes a 0 and moves to the right. If instead it was 1 over 0, it becomes a 0 and moves to the right. And if it was a 1 over 1, that becomes a 1 and moves to the right. And this is my final answer. All right. Eventually it gets to the end of the string, which will be a blank, and then this Turing machine will halt because I didn't say to do anything for a blank. And so it will end with just, whatever all the answers are will be written on the tape. So this is an easy example, I would say. The bitwise and. Any questions about that? Do you think you could do the bitwise or? I think you could. It's just very similar. I mean, it would be the same, really, only some of these would be different. Actually, these two zeros would be ones. That's the only difference if you're using or instead of and. All right. And any bitwise operation, there's also, the exclusive or there's NAND and NOR. You can do any of those very simply by changing these things around just a little bit. If you want to think of this sort of more mathematically, you could say basically this is a different, somewhat weird way of writing the truth table definition of what and means in logic. It's all the same kind of stuff. All right, that was the bitwise and. You can similarly do bitwise, all those other kinds of simple logical operations. How about, and this is really what I wanted to get to today that's more interesting, how about a bitwise add? All right, this is kind of like that bitwise and, only this time you have to carry, which makes things a bit more complicated. Let's try a bitwise add. So I have an example here, just so we can get a feel for how this works. I think those are the same numbers as I had before, whatever. And I want to add them now. So let's assume that the two numbers have equal amounts of digits so that you can stack them nicely. Of course, like I said before, if they don't have the same number of digits, you can always just insert zeros on the left side of one of them to make it big enough. It's not a big deal. Anyway, let's assume that the two numbers have the same amount of digits, and I want to add them. So what's the answer when I do bitwise add? You still more or less want to think of it digit by digit, although there is the issue of carrying. 0 plus 1 is a 1. 1 plus a 0 is a 1. If you think about it, I think really the only scenario in which you're going to have to carry is a 1 plus a 1, right? And if there is a 1 plus a 1, then the answer in that digit is a 0, and then you carry. All right? And in my next digit, I have a 0 plus a 0 with a carry, which means the answer is a 1. And then I don't have to carry anymore, and so I can go in the last digit I'm not carrying, and that's just a 1. All right, so that's the answer. You do have to keep track a little bit of the carries. I would say the way that I want to think about this is the answer that you get per digit. For instance, if it's 0 plus 1 and you were not carrying, the answer is a 1. But actually, if it was 0 plus 1 and you were carrying, the answer would be 2, which means you write a 0 and then you carry to the next step. The answer, what I'm trying to say here, is the answer down here depends on what these two numbers are, and it also depends on if you're carrying or not. So rather than this example where we just had one state, actually I'm going to have two states, one which represents we are not carrying and one which represents we are carrying, because it makes the answer different if you were carrying in the previous step versus not carrying. So my basic setup here is I have a no carry state. Sounds like I'm talking about guns. No carry in my classroom, please. And then we have the yes carry. All right. there's the no carry and the yes carry, and those things, like I said, the answer per digit is different depending on if you are carrying at that moment versus not carrying at that moment. All right. Actually, there's going to have to be another sort of a preliminary state because, if you recall, everybody knows when I'm adding these numbers up, actually you want to start on the rightmost end. So actually we need some stuff before this which just moves us all the way to the right so that we can get started properly. So I'm going to put that in here first. This is a beginning thing which, well, let me just say, like the basic structure that we're going to have is this goes in here and then these guys kind of go back and forth. Because from one digit to the next, maybe you carry on some of the digits, but then you don't carry on some other ones. Maybe you start off not carrying, but then you carry it later on. Anyway, this is the basic structure here. So the first state is just to move over to the left. And so this is just going to be a loop which goes all the way to the left, to the right. And then once I make it all the way to the end, I go BBL. So once I see a blank on the end, I back it up by one spot, and then I'm actually ready to start adding. And I make this start adding in the no carry state. That's because when you start in the first digit, you're not carrying yet. All right. You might carry in the future, but you start off not carrying. Anyway, what goes here? I have to move to the right past everything, and everything could look like all various kinds of stacked bits. So this could say 0, 0, and I, of course, want to leave it like it is. 0, 1, 0, 1, R, 1, 0, 1, 0, R, and 1, 1, 1, 1, R. All right, all of this just moves us over to the end so that we can start adding properly. And now, the good stuff happens here. In the no carry state, we're basically going to list off sort of like this. Just depending on what the two bits say, you say what the answer is. You replace them with the answer. For instance, 0 and 1 turns into a 1. We have to think about, let's actually just think about this as an example. 0 and 1 turns into a 1. So that arrow will look something like, 0, 1 becomes a 1. And then I move to the right. To the left, I mean, sorry, because we start all the way over here and we work our way back to the left. The question is, if I see this in my no carry state, where should the arrow go? Should it go back here or over here? And the answer is back here, they say. Yeah, if you just have to think, if I really do see a 0, 1, and the answer, I'm not carrying, so the answer is 1, am I going to have to carry in the next step? And the answer is no, you're still not going to have to carry. So we just have to think that through each time. Maybe I'll start with 0 and 0, right? The answer will be 0. I move to the left, and you don't have to carry anymore, right? If you see a 0 and a 0, you add them up, you get 0. You don't carry in the next digit. So that's why this arrow loops back to the no carry state. Okay, similarly with 0, 1, the answer is 1, and I don't carry. 1, 0, the answer is 1, and I don't carry. 1, 1, I do carry, so that's going to go up here, 1, 1. What should the answer be in this digit if you're adding 1 plus 1?
0.
It should be 0, and we should carry, which is why it's going on that arrow, and I go to the left. All right, great. So we've handled all of the no carry situations. What about the carry? So again, like some of these will be looped here, and then some will be on this edge here, and you just have to think through each of them. So in the carry state, what if I see a 0 and a 0? First of all, what should the answer be if I go 0 plus 0 and I was carrying?
1.
Then the answer should be 1, because it's a 0 plus 0 is 0, but you got to carry 1. And then should that go over here or over here? The question is, should we still be carrying into the next position, or have we sort of finished carrying and we go back here? I think we finished carrying. If I go 0 plus 0 with a carry, that does not create another carry, and so that should go back over here. So this, I'm going to put in this column, or it's not a column, 1L, right? If you were carrying and you added 0 plus 0, the answer in that digit should be 1, but you should not carry into the next digit. So I'm making it go back to the no carry state. All right? And we just have to think through each of the other ones. What about 0 and a 1? So think about, first of all, what's the answer in this digit? If you are carrying and you see 0 plus 1, what's the answer?
0.
Yeah, in this digit, the answer will be 0, because basically you're talking about 2, which means you write a 0, and then you carry again into the next digit. So that one goes here, right? Because this will cause the carry to continue. So this is going to be 0, 1. The answer will be 0, and I still carry. Same goes for 1, 0, right? Because addition is commutative. And then finally, what about 1 and 1? This is the extreme case. If I have 1 plus 1 in this digit and I'm also carrying, that all adds up to 3. How do I write that? 3 in binary is like a 1, 1. It looks like 11, right? So I'm going to write a 1 as the answer in this digit and then carry on to the next digit. So this says 1, 1, 1, like that. And that's how we do it. You got to think this through somewhat carefully, but that's how it works. Any thoughts about that? This is a bitwise adding Turing machine. Great. We have 9 minutes remaining. Sorry, there's one last thing here. Anybody feel like I left something out? There is one sort of little technicality here that can happen if, for example, you're doing what happens here? So the interesting thing is going to happen once I get all the way to the end. Actually, like the rightmost digits are not terribly interesting. It's here, right? I was not carrying. I added 1 plus 1. So what should happen on my machine, according to these rules, is it writes, that would be this arrow here, right? It's going to write a 0 here, go into the carry state, and read a blank. Now, according to the rules here, I have no rule for what happens with a blank here, and so the machine should just stop. But actually, that's not the right answer. So there should be a rule in the carry state for what to do if you see a blank. Any thoughts? What should I have done? Yeah? Just put a 1. Yeah, this would be an extra carry that carries like all the way off the left side of the number. That means there should be another digit that wasn't there before. You should insert a new digit on the left side, which is a 1. And then move left, I guess. I don't know. Then everything will stop. Do I need a similar blank rule for the no carry? This would mean you get all the way to the left and you weren't carrying anything. Well, I would say you don't need a rule there because you shouldn't make a new digit. I suppose you could put a 0 there if you want to, but I don't play like that. I don't write zeros on the left unless there's a good reason to. All right. I would like you all to try to do a subtracting Turing machine in our remaining 7 minutes. I don't know if that's enough time, but let's try subtraction. I give you a hint. There's going to be a borrow state and a no borrow state. That's how the subtraction is going to work. The structure of the machine will look very much like what we have here. It's just, the details are a little bit different. I'm going to just try and write out an example. How about, let's write out a subtraction. 1, 0, 1, 0, 1 minus 0, 0. 1, 1, 1. Let's try that. So on the rightmost digit, I go 1 minus 1 is 1. That's no funny business. Next, I have 0 minus 1, which involves a borrow. So a borrow means I go over here and borrow that guy and make this a 1. Now I have, now I'm thinking of this as like 2 minus 1, which means the answer is a 1 here. So if you're doing 0 minus 1, the answer in that digit should be a 1, and then you borrow. Now over here, I had 1 minus 1 as written, but I'm borrowing, so really it's more like a 0 minus 1, which means I've got to borrow that thing again. And this turns into something like a 2 minus 1, which is a 1. So this is going to be a 1 here. All right. And this now is a 0 with the borrow. Really, this needs to get borrowed again. And then this becomes like a 2, like a 1 because it got borrowed. This is a 1. I think I did that right. I'm not an expert of borrowing.
Can you explain that again?
Maybe. So this was a 0, but it got, this 0 here, I would say this 0 needs to borrow here to become like a 2. But it already got borrowed from a previous step, so really this 0 is like a 1. And I subtract and I get, it's like 1 minus 0, which is 1. All right. See if you can make up appropriate rules for that. I already said. You have this same thing at the beginning, which just moves everybody to all the way to the right. So don't worry about that part. The interesting part is this: no borrow versus borrow. Sorry, we only have a couple minutes. I think in the interest of time, we'll just have to, I'll just have to finish us off. Sorry, we only got a couple minutes. I hope that you thought through a few of these arrows. What about on the no borrow, the looped arrow there? What am I going to put there? The question is sort of, what are the possibilities for subtracting one bit from another where you don't end up having to borrow afterwards? What did somebody write on this one here? Somebody shout it out. Yeah, 1 and 1 does not result in a borrow. And also 0 and 0 does not result in a borrow. So I like putting them in some kind of numerical order. This would be 0 and 0 does not result in a borrow. The answer is just 0. That should be a L direction, sorry. What else? 1 and 1, she said, results in a 0. And then also I think 1 and 0. 1 minus 0 is 1. And none of those result in a borrow. The only situation when you actually need a borrow from a no borrow is 0 minus 1, right? So that goes up here, 0 and 1. And what should the answer be? 1, yeah. If it's 0 minus 1, you borrow, the 0 basically turns into a 2, and then you go 2 minus 1. The answer is 1. All right, great. And let's talk about the borrows. How about the arrow from borrow back to no borrow? So this would be, is there any scenario when you had a borrow, but after this step you don't have to borrow anymore? I think the answer is 1, 0. If there was a 1 in that digit, but it got borrowed, that means it really counts as a 0. But you can't actually do 0 minus 0, and you get 0, and then your borrow is over. So this looks like that. I think all of the other ones have to stay as continued borrows. And so over here, it should be 0, 0. If it's 0, 0, but that 0 got borrowed, you have to borrow again, and then it ends up really being like 1 minus 0, which gives you the answer of 1. Here, if it was 1 minus 0, no, I already did that one. That's the no borrow one. 0 minus 1. If that 0 got borrowed, You're going to have to borrow again. I believe this gives you a 0. And then if it's a 1, 1, this will give you a 1. Sorry to rush through those. It's time to go. These are a little tricky to think through each one if you're not used to borrowing, which I am not. All right. Hope you have a good weekend. You will have some homeworks for next time. Check them out.